This is the two-dimensional case, right?
Yes.
Now we are ended. So we actually prove the compactness result, right? Compactness. Now what is the consequence of the compactness result? What do we achieve? So here we're dealing with the Schrodinger equation because the conductivity equation is reduced to Schrodinger equation. Okay, so we talk about this equation. Okay, so and we are trying to get some kind of local uniqueness.
Yes. Yeah.
Okay, and what we have achieved so far.
If it's
So we
complete.
define so here P, Q, Q, right? We talk about this product of solutions, okay? And so what we have achieved. So what is the? I mean, we have proved some compactness result. Now, what is the relation between the compactness result with this set? What is the central conclusion we made?
If it's complete, then it's
So if
yeah.
okay, so this is complete
Then it's local unique.
in L2, let's say. Okay, then this imply what?
Local uniqueness.
Local uniqueness. So that's for you. So this will imply the local uniqueness near
Out of reference.
Q.
Yeah. Reference that's
Okay. Here and here in this case, when we talk about this local uniqueness business, we have to assume that the Q is in C1 of the box. So this is purely a technical assumption. Okay, a technical assumption. Okay. So anyway, so this is achievement. So now the question is, and for what Q, this is going to be complete, right? So for example, we know that when Q equals 0, then this
it's complete.
is complete. Because when Q equals 0, this is essentially become a
Harmonic.
harmonic functions. And the product of harmonic function is complete. Because we know the solution V equals E, C, and you choose two different C, right? You can turn this into a Fourier transform. And so there you can do it. Okay, so here is to see so how this guy, so this is a very restricted result because we would like to see for what kind of non-trivial Q this is also complete, right? So here what we're going to do is going to prove a generic local uniqueness. So this means that there exists open and a dense set all in the C1 on the bottom. Okay? It's an open set, but it's also dense. Okay? And so that the local uniqueness holds near Q for any Q in O. So that's this is not going to be the best result because eventually people achieve the global uniqueness. But here, what we're trying to introduce this old result is because we want to see the thinking, thought process, and also some technique. Okay. So this means that generically, the local uniqueness holds. Okay. So this means that or anywhere in the C1 space, no matter what potential you choose, there always a close enough potential so that the local uniqueness holds near the okay. So to achieve this, what we call the generic uniqueness, you need to show that basically you need to show that there is a dense and open set O. So another way to say it is so that PQQ is complete in L2 for all Q. Right? If you connect it to the compactness result, so this is all we have to prove. You need to show this is complete for all modular Q. Now here is a problem. So this PQQ, okay, this space is actually in L2 cell. Now this set is in L2, right? And the complement. So remember the Q perpendicular. So the perpendicular subspace. Now this this is going to be a UL2 omega, and this is a closed subspace. And we see that this closed subspace is finite dimensional. So this is what we call that. If you expand this guy, if you take this guy as a space, expand it into a subspace, okay, then this subspace has a finite codimension. Okay? So this is good news, but however, once you come to something like this, if you directly handle that, it's not easy because you think about subspace. Suppose you have a sequence, a function of subspace, okay, in L2, then this subspace may continuously, may change continuously, but however, dimension can jump. The dimension itself can jump up. So therefore, it's not easy to handle this directly. So what we're trying to do is we're going to reduce this. So you can see this is the order product of solution, right? So what we're trying to do is we're going to use the spatial solution to construct a smaller set of the product solution, then put them together. And that thing can behave nicely, which can handle. Okay, so this is the things we just actually we defined last time is an operator. So remember the V x k is equal to E c k x 1 plus omega x k. So C is equal to K perpendicular plus I K. Right? So this is a spatial solution satisfied these equations. Okay? So that's one kind of solution. And so V1 to V1 and omega 1 correspond to that. Then you take another spatial solutions. This equals to E C dot x 1 plus omega 2 x k. And this time C1, C2. So this equals to minus K plus I K. So maybe we have the whole thing about like 2, for instance, for simplicity. Now if you use these two spatial solutions, and you can see that this is the exact solution we use in the 3-dimensional space. The high dimension K to pull it over the surface, right? But here you have limited choice of the parameters, so there's only one K, there's no free parameter involved. So the 3D proof does not apply to the 2D case. But however, we're going to use this. I mean, we're going to consider the product, V1 and V2. So you can see this product will involve a free parameter K, right? Okay? But the set of all the K, so this is actually for K large enough. Okay, large enough, then the solution exists. So using these space solutions, you can construct the product which forms a subset of this PQQ. Small, but however, it's enough for us to get a generic. So that's the idea. So we're going to look at this this operator. I mean, you take the F. So we are thinking the F is something that is going to be perpendicular to the PQQ. Okay, suppose this. Then you can see if I take the F to the V11, multiply V11, then that's going to be equal to 0, right? So this thing equals to B11, B2, Bx will become 0. Okay? So then you can use the B11, you can see this can be written as the integrations, the F, E, then you have two exponential, so you multiply together. The C1 plus C2, so you just get the Fourier transform of that, the EIKX. Then you have the product of these two, which is you multiply out, you get omega 1 plus omega 2 plus omega 1 omega 2. Yes. Okay, so if you have a perpendicular F is perpendicular to the PQQ, then this is going to be 0. Okay, and from here we're going to construct operators, and in that case you can see that the F is going to be in the kernel of this operator. Then you can work on the operator. Okay, so now you can see that in order to, because you can see that here's a restriction. That means K has to be greater than K, right? Greater than this fixed constants, okay? And so therefore, so you have to, but so this one does not define for all K. So therefore I use cutoff functions called K greater than K, okay? And then multiply to this. Okay. Now, without omega 1 and omega 2, think about the harmonic, Laplace equation case. You can see this is exactly the Fourier transform. Okay. But here, because in the general case, you have to, this exists only for large K, so that's why we have to put a transform. Now, after multiply by this, I want to go back to F. So therefore, I'm going to take the inverse Fourier transform, okay? And for the inverse Fourier transform, they are for another polar function that's the restrict everything in the double polynomial. Okay, so you can see, I can think about this function F to here, to this one, to this, okay? So what is the connection between of this operator and the PQQ? Now from this relationship, you can see that if F is perpendicular to PQQ, this is going to equal 0, right? Mm-hmm. Then of course, this will also equal 0 for this F. So this means that the F is perpendicular to that. If this happens, then this implies that F has to be what? In the kernel of this operator. Okay. So from here, so this is the proof. Okay. So this is that. So if let's for the time being, let's call this operator. Let's say is called the. I don't have a notation, but I'll just call this.
I think it's box.
So what do you want to call it?
I think you used square last time.
Huh?
You used a square. That's what you did last time.
S cube?
Yeah, a box.
I don't remember. S cube, I said.
Okay.
S cube to the F. Okay. Right. Is that right? I don't think I assign any notation for this operator. Okay. Now this operator can be considered. Okay. So this apply to F, right? So S cube is considered L2 omega to L2 omega. Right?
Yeah.
It's a map to the same space. So here we get conclusion. If S cube, okay, is isomorphism, if S cube is isomorphism, then this implies that PQQ is right. I can make such a conclusion. Because why? Now, if SQ is isomorphism, then this means that the kernel only consists of zero potential. Okay? So therefore, there will be no F make this happen, because you have a non-trivial F make this happen, then this F will be in kernel. But I know that kernel is consists only trivial potential, so that's not going to happen. So therefore, to prove that the PQQ is complete, it's reduced to prove that the SQ is isomorphic. But actually, this is a little bit more than you need to prove, because what we really need to prove is that the SQ is what? What is the real things we want to prove? We want to prove actually is SQ is injective, right? If SQ is injective, the kernel is a trivial potential, and then probably not. But it happened that for this operator, if you can show this is a injective, it's the same as you showing it is isomorphic, because this operator has a very important properties. So that's what I'm going to show you. Okay. Okay. So if you take a look at here, you can see that you can rewrite this operator in two parts. Okay. First, slide into here, you have an important thing here, that's 1. So I separate 1 from the rest. Okay. So use the 1, so you can, this is the chi. Okay. Then you can see what's the rest. So using 1, you separate 1 from the rest. Okay, you put these together. And 1, isolate 1. So here, this one is what we want. Fourier transform of. Okay, it's the Fourier transform of F, right?
Yeah.
Then you take multiply to this cutoff function. Then you take inverse Fourier transform. Okay. So that's the first part. Then the other part is the omega.
Yeah.
F-E-I-K-X. Then omega 1 plus omega 2 plus omega 1 omega 2 dx. Okay. Okay, so here, last time we did something about these things. We did something about that. AQ, right? It's called AQ. But we prove an important property of AQ.
Compact.
No, it's not compact. AQ cell is isomorphic. Okay. But that fact, I guess, it turned out that it's just a consequence of that, okay? Of some argument later will be used. But this thing actually can be continued to split into two things. The first thing is, so this thing, I underline this thing, okay? Now here you can see, take the, suppose you don't have this type. Suppose you don't have middle cutoff function. So you start from F. F is L2, right? In the L2 omega. You take Fourier transform, okay? Then you take the inverse Fourier transform. Then you multiply by this cutoff function. What do you get? You go back to F, right? It's identical. Okay, so therefore this thing can be written as the F itself, okay? You minus the, another operator is this. You replace either K less or equal to K times F. Okay. You can write like this, right? So because if you look at the R2, okay, the complement of this is that, right? Okay. So now you can see that the operator we involve here goes to F minus and plus so previously, this part, underlying things, is basically now split into two things. Okay. So here, this one, okay, if you pay a little bit more attention about this operator, and we can see this easy to see that this is compact. This is compact operator. Why? Because if you take the let's think about F is in H1. Okay. Now here we're going to somehow define the Sobolev space using the Fourier transform, because Sobolev space is basically defined by the derivative, right? The weak derivative. Okay. So, but in the Fourier transform, this guy can be written. I mean, so this means that if you take the Fourier transform, then you multiply 1 plus k. Right? Then you take the inverse Fourier transform, you get the derivative, right? I mean, here it's not really the derivative, but it is equivalent to the derivative. So in order for f is equal to H1, so you need this guy is in L2. R2. L2. Okay. So that's equivalent condition. Okay. Now, suppose you're having a function like this, okay? So you take the f to, so here, f is in, starting from L2 over here. Okay. So you multiply to F here. So you can see that this is still in L2, right? L2, I mean in the K space, I mean L2, R2, right? And the norm is equivalent, the L2 norm will be equal, is that equal? Now if you multiply the cutoff function, so this guy is defined on the entire space. Now here what you do is you cut the rest of the function, the value of function. You just replace the value of this Fourier transform by 0 outside of the big disk, right? Mm-hmm. So this guy becomes complex supported. Now if this guy becomes complex supported, then you can see that I can multiply some additional things here. Then this guy was still in L2. Right? So what does it mean is that then you will take the inverse Fourier transform back. Okay? Then this function will be smoother than the previous one. Now this guy will become H1, right? So of course you make a restriction, and still H1 functions. And actually the norm can be controlled by L2 norm, starting from the beginning. Okay? So this means that if you start from L2, you're actually getting the H1 function. So by the invading here, you can see it has to be compact. Okay, it's a compact. That means for any bounded sequence in L2, this bounded sequence must carry some convergent subsequence by the invading here. So you can see that this is compact. Okay, so but the compactness of this part is easy to see. I mean, you can do the direct analysis to see this compact. Okay, the thing is here, this guy. Now, if you remember, we put the compactness result in the previous lecture regarding the local uniqueness. We're also facing the same things, right? So here we can also prove that this guy is also compact. But however, we're going to skip detail. There's some heavy estimate used in order to get it. So therefore, you can see that so the whole thing you can written like this: the F plus another operator called KQ plus F with KQ compact. With KQ compact. So therefore, if I put everything using the notation SQ to denote the entire operator, so you can see that SQ is written in I plus KQ. I is identity map, identity operator, and the KQ is compact. So what kind of operator is called this?
Federal. Oh no.
It's called federal. And actually in this book, in this yellow book, they have a nice introduction of the federal operator, and which is on page 71. Okay. So this is the important middle result we want to achieve. This is the federal operator. Okay. For any federal operator, there's an important property saying that this operator is isomorphism if only if the kernel carries only triple elements. Okay. So there's nothing